can you hear me? Yep, okay, great. Right, thank you very much. First of all, I'd like to thank the organisers for allowing me to talk about my work today. Sorry, do you see your own screen here? Like, I'm not like blocking the slides, am I? Oh, okay, no. Okay, that's fine. All right, I am Garvin Yim. I'm a PhD student of Ian Jones. I've just finished my PhD actually. And today I'll talk to you about F-mode oscillations from small spin-ups and spin-downs of neutron stars. And so first I'll begin with a quick summary of the electromagnetic observations. I'll begin with glitches. So glitches, if you imagine a spinning down neutron star, every so often it will spin up all of a sudden. So this is delta nu being positive, and simultaneously we'll get an increase in the spin down rate. So delta nu dot becomes more negative. And often what follows is an exponential recovery. These glitches and their recoveries are well documented, and they have models to describe them fairly well, which include the vortex unpinning model and starquake model. However, more recently, Espinosa et al. Reported the existence of some small timing events which did not fit the description of glitches, and they dubbed these glitch candidates and anti-glitch candidates. So as the name suggests, glitch candidates have a similar signature to glitches, so a positive change in the spin frequency and an increase in the spin down rate, whereas anti-glitch candidates are the opposite. And if we look at the figure on the right-hand side, we see on an axis of delta nu on the x-axis and delta nu dot on the y-axis that glitch candidates and anti-glitch candidates, which are indicated by the white and black dots, are much smaller in magnitude compared to glitches, which have which are these grey diamonds. And this is one of the key differentiators between glitch candidates and anti-glitch candidates. The second of these differentiators is that the glitch candidates lack an observed recovery, so are step-like. And the fascinating thing is that these events have been relatively unexplained. And so the point of my project was to try explain these observed phenomena. So we're preparing a paper right now, and it should be on the archive within the next week or two. And so looking at the graphic on the top, we start with a spinning down neutron star, which spins down on the order of a month, as this is the frequency at which these events occur. And during this time, elastic energy is being stored in the crust, and vortices are also being pinned to the inner crust. And all of a sudden, due to some threshold being crossed, a mode will be excited. And the mode which we'll assume is excited is L equals 2, M equals plus and minus 2 F modes. The plus or minus 2, it refers to whether the mode is going in a prograde direction or a retrograde direction. And this mode excitation happens on an instantaneous time scale. And because these modes cause a time-varying mass quadrupole moment, gravitational waves are emitted. And as a result, the mode decays on a timescale of around 0.1 seconds. And so the final result, the final configuration is the neutron star has gained some angular frequency due to the excitation and decay of these modes. Now, looking at the table at the bottom, this shows the cumulative change in the angular momentum across the three components that we're considering. So the neutron star will break up into the bulk of the neutron star, the modes, and we'll also track the gravitational waves which get emitted to infinity. And so during the three stages, which are indicated by the dashed lines, during the spin down, the bulk of the neutron star does spin down, but the change in angular momentum is negligible. But when a mode is excited, we say that delta J of angular momentum goes into the modes, and to conserve angular momentum, we must have that the bulk loses delta J. And finally, during the mode decay, one might initially think that only delta J can be emitted as gravitational waves, as that's how much is in the modes. But through careful calculation that was detailed in our earlier paper this year, we found that 2 delta J of angular momentum is radiated as gravitational waves. And so there's an extra minus delta J that the bulk gains. And so the net effects of the excitation and decay of a mode is that 2 delta J of angular momentum is emitted as gravitational waves, and the bulk changes angular momentum by minus 2 delta J. Delta J can be positive or negative depending on the sign of M, on whether it's retrograde or prograde. Okay, and so what does this model mean for the mode amplitude? So from the conservation of angular momentum, we can write the change in spin frequency in terms of the angular momentum that the mode is given. And the mode angular momentum is proportional to the square of the mode amplitude. And so we can rewrite the change in spin frequency in terms of the mode amplitude. And if we invert this equation, we can see what values the mode amplitude must be in order to explain changes in spin frequency. And so this is what we do for glitch candidates and anti-glitch candidates. And one further thing is we can look at the speculative case where glitches are also caused by this mechanism. Like I said before, there are already very well documented models for how glitches are caused, but one might also, in this model, we could propose that glitches are due to the excitation decay of a retrograde mode. So what's this mean in terms of the mode amplitude? Well, for the Crab and Vela pulsars, we get a mode amplitude of around 1 or 2 times 10 to the minus 6. So this means 1 part in a million change in the fractional radius of the neutron star. So it's around a deformation of around 1 centimeter. And for glitches, it's a little larger, especially for Vela, where we get a mode amplitude of around 1 times 10 to the minus 4. Now, there can actually be an upper limit placed on alpha, depending on gravitational wave observations. And so if, from 2011, there was a paper that looked at burst gravitational waves from a 2006 Vela glitch, and that placed an upper limit on H0, and the corresponding upper limit on alpha is 2.6 times 10 to the minus 4, which is 260 on this scale here. And so we can see that glitches are allowed observationally to be caused by this mechanism. So current observations now with O3 or O4 sensitivity should help constrain this a lot. So we're just going to connect gravitational waves. As I mentioned, there'll be a burst of gravitational waves with a timescale of around 0.1 seconds and a gravitational wave frequency of around 2 kilohertz. If we equate the standard quadrupole formula to the gravitational wave luminosity calculated for our modes, we find that the gravitational wave strain is linearly proportional to the mode amplitude, inversely proportional to the distance to the pulsar, and exponentially decays on the timescale tau. And for a non-observation, an upper limit can be placed in alpha, like I have just mentioned. And this is analogous to R mode. Okay, thank you for that. This is analogous to R mode searches where there's an upper limit on alpha. And this number here can help constrain the excitation models for these modes. And finally, just a word on detectability. Since we know what the signal will look like, it will be a damped sinusoid. We will quantify the detectability using the signal to noise ratio. And so the signal to noise ratio in terms of the mode amplitude is given by the top equation here. And the sensitivity used is that of the Einstein telescope at a frequency of 2 kilohertz. And since our model can connect a mode amplitude to a change in spin frequency, we can rewrite the signal to noise ratio in terms of a change in spin frequency. And putting in the values for glitch candidates, anti-glitch candidates, and glitches, we get a signal to noise ratio of around 1 for the Crab using the Einstein telescope, around 5 for Vela using the Einstein telescope. And since the threshold for detection is around 10, we can say that individual modes are unlikely to be detected. However, if we were to stack multiple modes coherently, then we might be able to improve the signal to noise ratio. What is interesting is that the signal to noise ratio for glitches, for Vela's glitches, are predicted to be around 4 to 500 for the Einstein telescope. So if we look at what the signal to noise ratio should be now, it's in the order of 40 to 50. And so the next burst search that's coincident with one of these glitch candidates with a glitch, I should be able to constrain this model greatly. So I'll just leave you with my conclusions here. We created a novel model to explain the small changes in spin and make connections to gravitational waves. Although the signal-to-noise ratios for the Einstein telescope are small for individual modes, it might be possible to accumulate enough signal-to-noise ratio for a detection if we were to stack a few signals. And as presented, the model only explains changes in spin frequency, and changes in the spin down rate will be considered in a separate paper. And there are numerous improvements to be made, such as modeling how the modes are excited, adding higher order rotational effects, modeling a more realistic interior, and also to include the effects of higher order modes. Thank you for listening.
Thanks very much, Garvin. We have one question in so far, which is, hi Garvin, lovely work. Do you have a sense if you would expect to see QPOs at the F mode frequency in the pulsar radio emission? If so, would you expect the amplitude of the QPOs to scale with the anti-glitch amplitude?
Right, okay. So I'm not too familiar with radio observations. However, what we're modeling here are timing events, which tell us, well, it's resolved in time. And the thing with the QPOs is, because these modes decay on like 0.1 seconds, that's about the order of like one or two rotations of a neutron star. And so we probably won't be able to see QPOs because the F modes themselves last such a short time. If we're talking about longer duration QPOs, let's say, I don't know, days or hours or whatever, I'm not too sure. But in our model, our neutron star essentially goes back to normal once the mode has fully decayed away. So I don't think we'd expect QPOs.
All right, thanks very much. I think in the interest of time, we will move on. But if anybody else has more questions, do ask them on the Slack.